Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to explain how to isolate the behavior of a single uncertain quantity defined in a model which contains multiple uncertain quantities. Let's get to it. The distribution of a single uncertain quantity is often called its marginal distribution, and we're going to be considering discrete random variables. Our goal is to answer the following question. In a model that contains multiple variables, how do we characterize the behavior of an individual variable? And again, we're going to be considering discrete random variables. As we explained in a previous video, the joint behavior of discrete random variables is completely characterized by the joint PMF. So what we're saying here is that we might have a joint PMF estimated from data, which contains the interactions between two random variables, in this case, A and B. But it's possible that we only are interested in what is going on with A. That is captured by the marginal PMF of A, which is just the PMF of A as a single random variable, which, remember, we denote by P with this subscript A, which says that the PMF is a PMF of the random variable A. If we want to find the entries of the PMF of A, how do we go about it? Well, by definition, the first entry, not the first entry, sorry, well, you can see it as the first entry, I guess, but the PMF evaluated at 1 just tells us the probability that A is equal to 1. So if you remember, we can compute the probability that the two random variables belong to a particular set, summing entries of the joint PMF. In this case, this set that we're interested in is just the event A is equal to 1, which contains these different possible vectors. 1, 2. Why do I start with 1, 2? That makes no sense whatsoever, right? 1, 1, 1, 2, and 1, 3. Right? The event that we're interested in at the end of the day is just the union of the individual events that A and B are equal to these three possible values. And if you remember, we can compute that by just summing the joint PMF over those values. So perhaps more intuitively, we want the probability that A is equal to 1. What do? We sum the probability that A is equal to 1 and B is equal to 1, plus the probability that A is equal to 1 and B is equal to 2, plus the probability that A is equal to 1 and B is equal to 3. Okay, and those probabilities add up to 0.55. That gives us an entry in this marginal PMF, which is just the PMF of the individual random variable A. So in general, when we want to compute the PMF of an individual random variable at a particular value, this is just equal to the probability that that random variable is equal to that value. And this is just the union of events of the form the random variable is equal to the value that we're interested in, and the other random variable is equal to every other possible value. So in the case of, in our very simple example, it was just 1, 2, and 3. It could be many, many more. You just need to sum this, the probabilities. Okay, I went maybe a little bit too quickly because we haven't introduced sums yet. You're considering the union of all of these events where A is equal to the value that you're interested in and B is equal to every other possible value in its range. And what I was getting at is that all of these events are disjoint, as we discussed in the previous video on multivariate discrete random variables, so we can just sum their individual probabilities, and those individual probabilities are all encoded by the joint PMF. So essentially what we're doing is we're summing the joint PMF over the other variable, because remember, we're interested in the probability that A is equal to that value, so that value is going to remain fixed, and then we're going to sum the joint PMF over the other value. Okay, and that's called marginalization in probabilistic models, and we obtain the marginal PMF, which is the individual PMF of the random variable A. Okay, so a picture to make things more intuitive. If we want the marginal PMF of A in this case, what are we going to do? We're going to sum over all the values of B for 1, 2, and 3. Okay, so the colors indicate that. This collapses to this PMF of A. you can check that this is going to give you a valid PMF, which is going to be non-negative and adds up to 1, and completely characterizes the individual behavior of A. Let's take a look at an example where we have two movies, Independence Day and Mission Impossible. And if you remember the video on multivariate random variables, we have their joint PMF. So we know, for example, that the probability that a user assigns a rating of 3 to Independence Day and 4 to Mission Impossible is 6.4%. Now, imagine that we're just interested in what people think of Independence Day. What do we do? Well, it's very easy. We just sum these probabilities over all the possible values of Mission Impossible. We sum them like this. And by the way, I think this is why marginal distributions are called marginal distributions, because people used to kind of sum them on the margins. And that's how they got that name. I don't know if this is actually true. You can check it online, but I believe that might be the case. Okay, so if we collapsed all of that, we get the marginal PMF of Independence Day. Of course, this always happens. I was explaining Independence Day, and now in the slides I had first decided to ask for Mission Impossible. It's exactly the same idea. We want the probability that Mission Impossible gets a rating of 1. We just need to add over all the possible ratings for Independence Day. Rating of 2, same thing. So when we add, in this case, across the columns, boom, we get the marginal PMF of Mission Impossible. I already explained that for Independence Day. We sum across the rows and we get that. And from this, we actually see, I went a little bit quickly, but people, it turns out, liked Independence Day more than Mission Impossible. That's not my perception, but then again, when I watched these movies, I was in Spain, and I think Independence Day might have rubbed Europeans a little bit the wrong way with all the patriotic stuff, so maybe that had something to do with it. But the point is that these marginal distributions capture the individual behavior of each random variable. Let's take a look at the case where we would have more random variables. For example, we have a 4-dimensional random vector. In this case, we can actually isolate the interactions between a subset of the entries of the vector, and that's also called a marginal distribution. In this case, for example, we have 4 dimensions, and we might be interested only in the interactions between the first and the fourth dimension. Okay, so how do we characterize that interaction? Well, through the joint PMF of only those entries. So now it's a joint PMF of 2 random variables. By definition, this is just the probability that the first random variable is equal to A and the fourth random variable is equal to D. So what do? We fix those 2 values, and now essentially what we want is the union of the events that those 2 values are equal to their fixed, those 2 variables are equal to their fixed values, and the other ones are equal to every possible value. So we're going to add over all the possible values of the second and third entries. We can sum this because these events are all disjoint. Okay, so now we just sum the joint PMF. Again, we sum it over the values that we want to get rid of, the ones that we don't want to fix, and we fix the values of the random variables from which we want to characterize the marginal distribution. We're going to look at an example in a moment, and actually right now. So we're going to describe the joint behavior of precipitation in Oregon in three stations: Corvallis, Coos Bay, and John Day. And now we're going to see whether we can isolate what's going on in each of them or in pairs. So we had this joint PMF that completely characterizes the interactions between the 3 random variables. For example, if we're interested in the probability that it doesn't rain anywhere, that probability is around 83%. If we're interested in the probability that it rains everywhere, that probability is 0.8%. Okay, this rarely happens. Now we want to isolate what happens in pairs of places. So we don't care about John Day, we only want the joint distribution of Coos Bay and Corvallis. So imagine, for example, So what is this joint distribution going to be characterized by? The joint PMF of Coos Bay and Corvallis. What are the entries of the joint PMF? The probability, for example, that Coos Bay and Corvallis are equal to 0 and 0. So it doesn't rain in Coos Bay or Corvallis. How are we going to get that probability? We're going to add the two values for John Day that corresponds to Coos Bay equals to 0 and Corvallis equal to 0. Adding those two values are going to give us that entry of the joint PMF. For the other entries of the joint PMF, we do something very similar. Coos Bay 0 and Corvallis 0 requires having these two values, and so on and so forth. I really recommend that you do this on your own. Try to derive the joint PMF of Coos Bay and Corvallis on your own. You'll see that you have to sum over the possible values of John Day, and you're going to get this joint PMF. And you have to check that you do get a 2x2 joint PMF, which characterizes the joint behavior of Coos Bay and Corvallis. What if we want Coos Bay and John Day? Well, there's similar idea. Now we want Coos Bay 0, John Day 0. These are the two values for which that happens. So we sum over them. What are we doing? We're summing over Corvallis. Okay, so it's a very similar idea. We're going to end up with this marginal joint PMF. We want Corvallis and John Day. For example, Corvallis 0, John Day 0. Corvallis 0, John Day 0. We're going to sum over the two possible values of Coos Bay. So we always sum over the variable that we don't care about, if that makes sense. And we would get that value. What if we want within this model only to characterize the precipitation in Coos Bay? We want, for example, the probability that it does not rain in Coos Bay. What do we need to do? We have to add sum over all the possibilities where Coos Bay is equal to 0, which are all of these guys. If we want the probability that Coos Bay is equal to 1, we sum over these guys. Again, I really recommend that you pause the video and do this on your own and compute the two probabilities. It should look something like that, actually. You can't see the actual values here, but I hope you get the idea. Okay, you sum over the values that I said. What if you just want Corvallis? Well, then you look the values for which Corvallis is equal to 0, and you sum over them. Again, you sum over everything that you don't care about. For Corvallis equal to 1, these are the values. We're summing over Coos Bay and John Day. All right, and we would get that marginal PMF. This allows us to compare what's going on in Corvallis and John Day, or Corvallis and Coos Bay, kind of separately, right, in terms of their marginal distributions. Finally, John Day. You were interested in John Day being equal to 0. We have to sum over the corresponding values. And if we're interested in John Day equals to 1, I think you get the drill, right? We sum over the values for which John Day is equal to 1. And that's it. It's as easy as that. When you want to isolate the individual behavior of random variables within a probabilistic model that contains many random variables, you just sum over everything that you don't care about, and that's going to give you the corresponding marginal PMFs. I hope that was clear. Thank you very much.